Hello dear students, let's see this question 1.1 of IE Irodov. So this question states, a motor boat going downstream overcame a raft at a point A. Tau is equal to 60 minutes later it turned back, and after some time passed the raft at a distance L is equal to 6 km from the point A. Find the flow velocity assuming the duty of the engine to be constant. This is a 1D river problem. So there is a river, and suppose this river is flowing with a velocity Vr, and there is a motor boat flowing there also. So I just want to write one result of river problem, and that result is the velocity of motor boat with respect to ground is equal to velocity of boat with respect to river plus velocity of river. And because this is a 1D problem, so we can do the direction part by just plus and minus. So there are two cases. In case 1, when the boat is flowing along downstream direction, in the direction of river flow, then the velocity of boat with respect to river is in the same direction with that of the velocity of river. So they are in the same direction. So we can just write VB is equal to VBR plus Vr when boat is flowing along downstream direction. And when the boat is moving upstream opposite to direction of flow of river, so VBR is opposite to Vr, and VBR is more than Vr if it has to actually go opposite to the direction of flow of river. So the magnitude of VB would become VBR minus Vr when the motor boat is going along the upstream direction. So this result we will use. So now let's look the whole picture from the ground frame. And in the ground frame there is some fixed point A, and there is a raft. Raft is obviously some wood or something like that, which is flowing by the stream of the water river. So the velocity of the raft is nothing but that of equal to the velocity of river. So the raft is moving with velocity of river in the ground frame, and at t is equal to 0, motor boat B overcame the raft, and it was coming from this direction, and so it overcame the raft. And in the downstream direction, obviously the velocity of this boat, velocity of boat along the downstream direction is this velocity is the VBR plus Vr, and obviously this is more than Vr, so it will overcome and go past it. So it is going like that, and at the same time raft is going like that. So at some later moment, t is equal to tau, this raft turned back. The raft turned back, and then now it is moving like that. After turning back, the direction has become upstream, and all the while the raft was going like that, and at some moment they met again. So the raft and boat, let's assume that they met at time t is equal to t from the beginning. So this is the moment they met, and it is given in the question when the raft met the boat again. The distance traveled by the raft is L. So distance traveled by raft is L, means this distance is L. So total time of motion for the raft is t. At time t, the raft met boat again. So we can simply write L is equal to Vr into t, and we have to find the flow rate, mean the flow velocity, mean the velocity of river. So Vr is equal to nothing but L by t. So if we can know the total time of motion, mean that the time interval between the first meeting of the crossing of the boat with the raft and again the raft boat meeting the raft again, that time interval is t. So that if we can find, we can simply find the VR. So here, so the first part of the boat was a downstream. In the downstream, the velocity of boat was VBR plus VR. And then the second part, after it turned back, that motion is the upstream, along upstream. So along upstream, the velocity of boat with respect to ground is VBR minus VR. So let me find the two more distances. The one distance, the distance traveled by boat during the upstream motion. So during upstream, the total time is tau and the velocity is the VBR plus VR. So this distance is VBR plus VR multiplied by time interval, which is tau. And then another distance is the distance traveled by the boat during the upstream motion. The time interval of the upstream motion, this is the time moment tau, this is time moment t. So the time interval for the upstream is the t minus tau. So during this time the distance traveled is the speed VBR minus VR multiplied with the time interval, which is t minus tau. So let's see some geometrical consideration. So we can clearly see that this distance is the sum of this distance and this distance. So VBR plus VR tau is VBR minus VR t minus tau plus L. And L is how much? L is VR into T. So plus VR into T. So let me open this. So this is a VBR tau plus VR tau, and this is VBR T minus VR T and minus VBR tau plus VR tau, and from here VRT. So this VRT cancelled, and this VBR tau will go to that side, so that will become twice VBR tau, and this VR tau and this VR tau will also cancel. So what is remained here is the VBR T. So we have a relation between T and tau. So T is the 2 tau from here. So this T is equal to 2 tau. So VR is L upon 2 tau, and this is our answer. We can put the value of L numerical value, and we can also put the numerical value of tau. So we'll get the numerical answer also. So this is our answer. But there is another way out. We can get this result T is equal to 2 tau quite easily. If you look the whole picture also in the river frame. So let's see that picture also. So let's see the picture also in the river frame. Velocity of raft with respect to ground is obviously equal to the velocity of river. So velocity of raft with respect to river is obviously 0. So because it is flowing with the velocity of river. So in the river frame, the raft will be at rest. So in the river frame, raft is at rest, and at t is equal to 0, the boat overcame the raft. Velocity of boat with respect to river is VBR, and it is written in the question that the duty of engine is constant. So the speed of the boat with respect to river is constant, only the direction will change. So in the downstream direction, when it was moving, so the velocity of motor boat with respect to river is the VBR, and which is constant. So at t is equal to 0, this motor boat overcame the raft, and at time t is equal to tau it turned back and met again the raft at t is equal to t as I had written there, assumed there. And we know that time interval between two movements is independent of frame of reference. So this time is same what is in the ground frame, that is also in the river frame. But when it goes in the upstream direction, the speed of the boat with respect to river is still the same because the duty of the engine is constant. So whatever distance it has traveled during downstream, that same distance it has traveled in the upstream direction and also with the same speed. So this time interval is equal to this time interval, or the whole time interval is double of this time interval. So here we can directly say without any equations that overall time of motion is twice of the time of motion during the downstream phase of motion. So t is equal to 2 tau, and then putting here we can directly get Vr is equal to L upon 2 tau in a much shorter way. Let's see question number 1.2 of Irodov. So this question states a point traverses half the distance with a velocity v0. The remaining part of the distance was covered with a velocity v1 for half the time and with velocity v2 for other half of the time. Find the mean velocity of the point average over the whole time of motion. So suppose the motion is from A to B, and the motion from A to B is divided into two equal parts in terms of length. So suppose this part AC is of length S and CB is also length S. In the first part, the velocity is V0. The second part is again divided into two parts in terms of time. Suppose there is one point D such that time taken from C to D is equal to time taken from D to B. Suppose the time taken in the first part A to C is T1 and overall time taken in the second part CB is T2, and the CD and DB are equal in terms of time. So the overall time from C to B is T2, so time taken in C to D and D to B are T2 by 2, they are equal. And in these parts velocities are V1 and V2 respectively as given in the question. So we have to find the mean velocity of the whole journey for the whole motion. So we know that the mean velocity or the average velocity is the total displacement upon total time. So total displacement for the whole motion is S plus S. So this is 2S. And total time is T1 plus T2. So total time is T1 plus T2. And in this part AC, velocity is constant. So we can write the S is equal to V0 into T1. So T1 is equal to S by V0. That is the first thing. So here 2S in place of T1 I can write S by V0, and now to find T2. So now the part CB, the CD part has suppose length S1 and DB part has length S2. So we can write the whole for the whole CB part S is equal to S1 plus S2. In the S1 part, particle is moving with velocity V1 for time T2 by 2. So S1 is equal to V1 T2 by 2. And similarly in the part dB, length is S2. velocity is v2 and time is t2 by 2. So this is v2 t2 by 2. So we can take t2 by 2 common. So that will be v1 plus v2 into t2 by 2. So from here we can take solve t2. So t2 will be 2s divided by v1 plus v2. And now we can put this t2 here. So this t2, putting this t2 here, so that will be 2s divided by v1 plus v2. And now this s will get cancelled. So we will remain with 2 upon 1 by v0 plus 2 upon v1 plus v2. Further simplification, 2 upon take v0 into v1 plus v2 as LCM. So we will get v1 plus v2 plus 2 v0. So finally we will get average velocity equal to, this will go into the numerator. So 2 v0 v1 plus v2 divided by v1 plus v2 plus 2 v0, and this is our answer. Hello dear students, I am going to discuss question number 1.3 of IE Irodov. So this question states, a car starts moving rectilinearly, first with acceleration omega. The initial velocity is equal to 0, then uniformly, and finally decelerating at the same rate omega, and comes to a stop. The total time of motion equals tau. The average velocity during that time is v average. How long does the car move uniformly? So this is a question of rectilinear motion, 1D rectilinear motion. So in this question, the motion has 3 phases. The first phase is the phase of a uniform acceleration, and then the phase of uniform motion, and finally the phase of uniform retardation, and comes to rest. So let's start with drawing the velocity time graph, and this is a very standard case of the velocity time graph. So I am drawing the velocity time graph for the given situation. So on the y-axis I have shown the velocity, and on the x-axis I am showing time. So first phase is a phase of uniform acceleration starting from the rest. So acceleration constant, so slope of velocity time graph is the acceleration, and because velocity is constant, acceleration is constant, so this would be something like this, and this is a of acceleration omega. Suppose this phase is of time interval t1 and reaches a maximum velocity, say v max, and then travels with this maximum velocity for some time, and let me assume that time to be, this time to be t naught, and actually we have to find this time only. So now it starts retarding uniformly with the same magnitude of retardation as that of the magnitude of acceleration. So retardation in this phase is also omega, and let me assume that this time to be t2, and overall time of motion is given in the question equal to tau. So let me write this A, B, C and D. So first of all, for this phase of acceleration, if I write the first equation of motion, v is equal to u plus at, reaches a maximum velocity v max, initial velocity 0, acceleration is omega, and time we have assumed to be t1. So t1 will be from here v max by omega. This is for the phase of acceleration from A to B. And similarly for the phase of retardation. So retardation is omega, so acceleration is actually minus omega. So for the For this phase, I will apply the same equation v is equal to u plus at. So final velocity is 0. Initial velocity here is v max. Acceleration is minus omega. And time interval is t2. So t2 is equal to v max by omega. So what we can see that the time interval for the phase of acceleration and the time interval for the phase of retardation are equal. So t1 is equal to t2 is equal to v max by omega. And total time of motion is tau, and this is t naught. T naught is the time interval for the phase of retardation. So the total time of the phase of acceleration and phase of retardation added together is tau minus t naught, and because they are equal, so this time can also be written as tau minus t naught by 2. This is tau, this is t naught, t1 plus t2 is tau minus t naught, they are equal, so t1 and t2 are tau minus t naught by 2. And now another thing that is given, that average velocity for this whole motion is v bar. So we know that the average velocity is equal to total displacement divided by total time. So we can also write average velocity is equal to total displacement multiplied by total time, and total time of motion is how much? Total time of motion is tau. So I am writing this v average into tau is equal to total displacement. And we know that in the velocity time graph, the area under vt curve is the displacement. So this whole area is the displacement. So this area can be divided into three parts: part 1, part 2, part 3. So first of all, the area of the part 3. So area part 3 is the altitude upon this base. So this is the v max into t naught, and this area is v max into t1 by 2, and this area is also v max into t1 by 2, and t1 and t2 are equal, so they added together are v max into t1. V max t1 by 2 plus v max t2 by 2, and t1 t2 are equal, so that is this. So this can be written v max t naught plus t1. And what is value of v max? Value of v max, we can write v max from here, this from here. So v max can be written as omega tau minus t naught by 2, and t1 is how much? T1 is this tau minus t naught by 2. Further simplifications: omega tau minus t naught by 2, and that would be 2 t naught plus tau minus t naught by 2. So this 2 into 4, and I want to take that 4 to that side, so that will become 4 v average tau is equal to omega tau minus t naught, and this is how much? Tau plus t naught. So this thing will become tau square minus t square, taking on that side, or still I can keep on this side, no problem. So this is omega tau square minus t naught square. We have to find t naught. So from here I can write t naught square is equal to tau square minus 4v bar tau by omega, and I can take tau square common. Tau square taken common will become 1 minus 4v average upon omega tau, and now take the square root. So finally we will get the time interval during which this particle or the body moves uniformly, which is t naught, which I assume, and that will come out to be taking a square root, tau square root of 1 minus 4 V average divided by omega tau, and this is our answer. Hello dear students, I am going to discuss question number 1.3 of IE Irodov. So this question states, a car starts moving rectilinearly, first with acceleration omega. The initial velocity is equal to 0, then uniformly, and finally decelerating at the same rate omega, and comes to a stop. The total time of motion equals tau. The average velocity during that time is V average. How long does the car move uniformly? So this is a question of rectilinear motion, 1D rectilinear motion. So in this question, the motion has three phases. The first phase is the phase of a uniform acceleration, and then the phase of uniform motion, and finally the phase of uniform retardation, and comes to rest. So let's start with drawing the velocity time graph, and this is a very standard case of the velocity time graph. So I am drawing the velocity time graph for the given situation. So on the y-axis I have shown the velocity, and on the x-axis I am showing time. So first phase is a phase of uniform acceleration starting from the rest. So acceleration constant, so slope of velocity time graph is the acceleration, and because velocity is constant, acceleration is constant, so this would be something like this, and this is a of acceleration omega. Suppose this phase is of time interval t1 and reaches a maximum velocity, say V max, and then travels with this maximum velocity for some time, and let me assume that time to be t naught, and actually we have to find this time only. So now it starts retarding uniformly with the same magnitude of retardation as that of the magnitude of acceleration. So retardation in this phase is also omega, and let me assume that this time to be t2, and overall time of motion is given in the question equal to tau. So let me write this A, B, C and D. So first of all, for this phase of acceleration, if I write the first equation of motion, V is equal to U plus AT, reaches a maximum velocity V max, initial velocity 0, acceleration is omega, and time we have assumed to be t1. So t1 will be from here V max by omega. This is for the phase of acceleration from A to B. And similarly for the phase of retardation, so retardation is omega, so acceleration is actually minus omega. So for this phase I will apply the same equation, V is equal to U plus AT. So final velocity is 0, initial velocity here is V max, acceleration is minus omega, and time interval is t2. So t2 is equal to V max by omega. So what we can see that the time interval for the phase of acceleration and the time interval for the phase of retardation are equal. So t1 is equal to t2 is equal to V max by omega. And total time of motion is tau, and this is t naught. T naught is the time interval for the phase of retardation. So the total time of the phase of acceleration and phase of retardation added together is tau minus t naught, and because they are equal, so this time can also be written as tau minus t naught by 2. This is tau, this is t naught, t1 plus t2 is tau minus t naught, they are equal, so t1 and t2 are tau minus t naught by 2. And now Another thing that is given, that average velocity for this whole motion is v bar. So we know that the average velocity is equal to total displacement divided by total time. So we can also write average velocity is equal to total displacement multiplied by total time, and total time of motion is how much? Total time of motion is tau. So I am writing this v average into tau is equal to total displacement. And we know that in the velocity time graph, the area under vt curve is the displacement. So this whole area is the displacement. So this area can be divided into three parts: part 1, part 2, part 3. So first of all, the area of the part 3. So area part 3 is the altitude upon this base. So this is the v max into t naught, and this area is v max into t1 by 2, and this area is also v max into t1 by 2, and t1 and t2 are equal, so they added together are v max into t1. V max t1 by 2 plus V max t2 by 2, and t1 t2 are equal, so that is this. So this can be written V max t naught plus t1. And what is value of V max? Value of V max, we can write V max from here, this from here. So V max can be written as omega tau minus t naught by 2, and t1 is how much? T1 is this tau minus t naught by 2. Further simplifications: omega tau minus t naught by 2, and that would be 2 t naught plus tau minus t naught by 2. So this 2 into 4, and I want to take that 4 to that side, so that will become 4 V average tau is equal to omega tau minus t naught, and this is how much? Tau plus t naught. So this thing will become tau square minus t square, taking on that side, or still I can keep on this side, no problem. So this is omega tau square minus t naught square. We have to find t naught. So from here I can write t naught square is equal to tau square minus 4v bar tau by omega, and I can take tau square common. Tau square taken common will become 1 minus 4v average upon omega tau, and now take the square root. So finally we will get the time interval during which this particle or the body moves uniformly, which is t naught, which I assume, and that will come out to be, taking a square root, tau square root of 1 minus 4v average divided by omega tau, and this is our answer. Today I am going to take question number 1.4. So the question states, a point moves rectilinearly as shown. S is the distance traveled as a function of time t. Using the plot, find average velocity during time of motion, maximum velocity, time movement t naught, at which instantaneous velocity is equal to the mean velocity average over the first t naught. So first thing, we need to know that the particle is moving on a straight line. So suppose this is the line on which the particle is moving, and this is the S is the distance traveled. S is the distance traveled, and this is the distance time graph, and is always increasing. It always increases. Uh, the particle is not turning, so whatever is the displacement, that is same as the distance. So we can think of this as also the displacement time graph. So S is the displacement till time t. So this is our S, and we know that the slope of the displacement time is equal to the velocity. So we can mark the three phases of the motion. This is the phase AB is the first phase, then BC is the second phase, then CD is the third phase, and there is part D also. So we can see that for part AB the slope is continuously increasing. It means the speed is increasing. It means that in this phase the particle is accelerated. In a part BC the slope is constant, it is a straight part, the velocity is constant. And in the part CD the slope is decreasing, so it is speed is decreasing. Speed decreasing means there is a retardation. And then in the part DE the slope is zero, it is straight line parallel to the t axis. It means the particle has stopped, particle is not moving, the motion has ceased at point D. So this is at t is equal to 0, S is 0, and then at t is equal to 10 seconds the particle has come up to here, so this is a 0.4 meter. So at t is equal to 10 seconds the particle has reached up to 0.4 meter and speed is increasing. So in this phase there is a acceleration in this direction, whether uniform non-uniform we do not know. And so from here to here speed is increasing. So far the speed at this point will be the maximum. This is the maximum speed. And then in the phase BC, which lasts for this is a 2 second, 4, 5 and so on. These are the 2 second intervals, so that is a 14 second. So till 14 second at t is equal to 14 second, the position it has reached is this is 1.4. So it has reached to S is equal to 1.4 meter, and till here it is moving with the same constant speed, and which is the maximum. Acceleration is 0, and at t is equal to 20 second. At t is equal to 20 second, the particle has reached S is equal to 2.0 meter, and here speed is decreasing, so there is a retardation. So there is a retardation. Acceleration is in this opposite direction. Retardation. Now, what is the average velocity for this whole motion? So average velocity is the total displacement upon total time. So total displacement is how much? Total displacement is 2 meter, and time is 20 seconds. So the average velocity is 0.1 meter per second. Then the second part asks, what is the maximum velocity? The maximum velocity is in this part. So the maximum velocity, because the velocity is constant, so this maximum velocity is also equal to the average velocity in this interval, or the slope of this line. So if I join these 2 points, So this thing is, this gap is how much? This gap is 1 meter. 1.4 minus 0.4, and this gap is 4 seconds. So the maximum velocity Vmax is the average velocity in this interval. So which is 1 meter divided by 4 seconds. So that will be 0.25 meter per second. And then the last part. The time movement at which instantaneous velocity is equal to the mean velocity average over the first t naught time. From this graph, instantaneous velocity at any moment is nothing but the slope at that point, and the average velocity from starting till a point is the slope of line joining initial point to that point. So now to find this thing, what I want to do, at different moments I am drawing some line from the starting. Suppose here I join this. From here to here, the slope of this line is the average velocity from this point to this point. But the instantaneous velocity here is the slope of this tangent, so these are not equal. This slope and this slope is not equal. Similarly, if I come somewhere here, the slope of this line is equal to the average velocity from here to here, but the instantaneous velocity is somewhere here. So, and similarly if I come here also, the slope of this line is the average velocity from here to here, but the instantaneous velocity here is the slope of tangent here, which is this slope, which is not the same. So it will occur somewhere here. So if I draw a line from here which is tangent to this part CD, suppose if I draw a line something like this, so it is tangent here. So the slope of this line is the average velocity, and tangent at this is a tangent here, and the slope of this tangent is the instantaneous velocity. So instantaneous velocity at this point is equal to the average velocity from here to here. So this is the this is the moment of time where the instantaneous velocity is exactly equal to the average velocity from starting till that point. So this point is going to come from somewhere here to here. So if I draw a proper scale, so we'll get that point. So it is somewhere between this point and this point. So around 16, something like that, we'll get that point. So that will be the answer to this part. Hello dear students. In this video, I am going to discuss question number 1.5 of IE Irodov. So the question states, two particles 1 and 2 move with constant velocities v1 vector and v2 vector. At the initial moment, their radius vectors are equal to r1 vector and r2 vector. How must these four vectors be interrelated for the particles to collide? So this question can be done in two ways. One is to do in the ground frame, other in the frame of either particle. So why we can do this question different frame? Because if the collision is happening, so it will, if it is happening in the ground frame, so it will also happen in the particle frame also. And the question will be highly simplified if we do in the particle frame. So suppose we have two particles, say particle 1 and particle 2, like this, and they are moving. This is a ground frame, they are moving something like this, and they collide somewhere. So collision means the arriving at the same position, same time. So this is what happening in the ground frame. And suppose this is particle 1, this is particle 2, And now let's look the whole picture in the frame of particle 1. So this is particle 1 and this is observing particle 2. So when this is observing, so with respect to itself, it is at rest. Now it is observing. So particle 2 must definitely move directly towards particle 1. Only then it will collide. If it will go something like that, it will miss. It will go something like that, it will miss. So the only condition for the collision, if they are moving with a constant velocity in the ground frame. So if you look the picture of particle 2 in the frame of particle 1, so particle 2 must always be coming directly towards particle 1. Only then collision will happen. The same thing will happen in the particle 2 frame. If you look the picture of particle 1 from the frame of particle 2, so particle 1 must always be coming towards particle 2, only then collision will happen. So now I am drawing this picture in the frame of particle 1 at a general moment. So suppose this is a particle 1 at a general moment and this is a particle 2. So particle 1 is observing, so this is a frame of particle 1. So what particle 1 will observe the position of particle 2? So from the concept of relative motion, so this will say that the position of particle 2 right now is vector r21. This is the position of particle 2 as seen from particle 1. And we know that r21 is equal to r2 minus r1. r2 vector is the position vector of particle 2 from the ground frame and r1 vector is the position vector of particle 1 in the ground frame. And as I explained just before, the collision has to happen. The particle 2 must directly go towards particle 1. So the velocity of 2 with respect to particle 1 should be directly towards particle 1. So this should be v21 vector. And what is v21 vector? v21 is the velocity of 2 with respect to 1. So v21 vector is v2 vector minus v1 vector. They are not equal, but if we look at, if I make a unit vector of v21, so this is the unit vector of v21, that is a v21 cap, and this is the unit vector of r21. Because they are unit vector, they have the same magnitude unity and directions are opposite. So v21 vector is opposite to r21 vector. It means the unit vector of v21 is negative of that of unit vector of r21 vector. So I can write r21 cap is negative of v21 cap, and we know that the unit vector of any vector is equal to that vector divided by its magnitude. So this unit vector can be written as r21 vector divided by magnitude of r21, and similarly this can be written as v21 vector divided by magnitude of v21. And now I can write r21 equal to r2 minus r1, and r21 magnitude is the mod of r2 minus r1 vector, and minus v21 will be v1 minus v2, and the magnitude of v21 is same as the magnitude of v1 too, and this means mod of v1 vector minus v2 vector. And this is our answer, and this answer can be written in so many different ways, and one of the ways is this. Dear students, let's see question number 1.6 of Irodov. So this question states a ship moves along the equator to the east with velocity v0 equal to 30 km per hour. The southeastern wind blows at an angle phi is equal to 60 degree to the equator with velocity v is equal to 15 km per hour. Find the wind velocity v dash relative to ship and the angle phi dash between the equator and the wind direction and a reference frame fixed to the ship. So this is a question of relative motion, and there is a ship, there is a wind, and we have to find the velocity of wind with respect to ship. So we'll write a result of relative motion at the velocity of wind with respect to ship is equal to velocity of wind minus velocity of ship. Or we can also write that is equal to the velocity of wind plus minus of velocity of ship. And so there is a ship. Ship is moving along the equator, along the east direction. Suppose this is the equator. And this is north direction, and this is east direction. The ship is moving along equator along the east direction with velocity v0. So this is the this vector is the velocity of ship. Its magnitude is v0. The southeastern wind. What is a southeastern wind? A wind that is coming from the southeast, between south and east. So this is south and this is east. So that wind that is coming from somewhere here. So that wind is coming from here and making angle phi from the equator. So this is the equator and making angle phi from the equator, something like this. So this is the wind that is coming. So the wind is, this is wind, this is the wind. Velocity of wind making angle phi. The numerical value of phi is 60. This is phi, so this is phi. So what we have to find? We have to find the velocity of wind with respect to ship, magnitude, direction. So in the next diagram, before doing that, what we can do, we can make and magnitude of this wind vector is how much? Is just v. So we can make the components of this vector along west and north. This will be v cos phi, and this would be v sin phi. I have to add the minus v shape vector to this vector. If I will add minus v shape vector, mean I will just reverse this vector in this direction, then add. So what we are going to get finally, again this is north direction, this is east direction, so v0 plus v cos phi. So in this direction that will be v0 plus v cos phi, and this direction this is v sin phi, and their vector sum would be something like this. And this is the vector, this is the vector velocity of wind with respect to ship. So this is velocity of wind with respect to ship, and it is named in the question v dash, and we have to find the angle between the equator and the wind direction, and this angle is phi dash. So the magnitude of v dash we can get from the Pythagoras theorem, square root of this square plus this square. So v dash is the square root of v0 plus v cos phi whole square plus v sin phi whole square. So that would be v0 square plus v square cos square phi plus v square sin square phi will be only v square, and the cross term 2v0 v cos phi. And the given value of the v and v0 which are given, v is equal to 15 km per hour, v0 30 km per hour, phi is equal to 60 degree. You will put that value, will get this numerical answer to be 40 km per hour. And the direction part, the phi dash, so tan phi dash is this by this, and this is the v sine phi, and divide by v naught plus v cos phi. So this phi dash is equal to tan inverse of this, and again putting the numerical value and looking from the scientific calculator or from the trigonometric table, you will get this answer to be 19 degree. That is our answer. So let's see question number 1.7 of Irodov. The question states, two swimmers leave point A on one bank of the river to reach point B lying right across on the other bank. One of them crosses the river along the straight line AB, while the other swims at right angles to the stream and then walks the distance that has been carried away by the stream to get to the point B. What was the velocity u of his walking if both swimmers reach to the destination simultaneously? The stream velocity is v naught and the velocity of each swimmer with respect to water is v dash. So as it is clear from the question that there is a river, I've already drawn the river. So there is a river, and let's assume width of the river is say d, and this width is not given, and this is just a intermediate term for us for calculation. And there are two fixed points A and B on the opposite shores, and the line joining AB is perpendicular to the river flow, and river is flowing with a uniform velocity. The velocity of river is say VR, and VR is given in the question to be, what is VR given? Value of VR given is v naught, that is the flow velocity of the river, and there are two swimmers and there are two cases, and in both cases the velocity of each swimmer with respect to river, that is the VMR, is also constant, is also same, and VMR velocity of a swimmer with respect to river is given to be the v dash for the both cases. So this is a case 1. Here is the swimmer 1. So swimmer 1 starts swimming from point A and crosses the river and reaches to the point B. So he crosses the river perpendicular to the river flow. So his velocity with respect to ground must be obviously towards AB, only then he will start from A and will reach to the A. So his resultant velocity means the velocity with respect to ground, that is the Vm. So velocity of this swimmer with respect to ground Vm must be towards starting from A and directed towards B, only then he will be able to reach to B. But river is flowing like that, so how can he start from A and reach to B? Only if he starts swimming like this. He attempts to swim like this, and there is a river flowing, so the combined effect of man swimming along this direction and river flowing along this direction will make his resultant velocity along this direction. So he must swim at some suitable angle, at some suitable direction like this. So suppose he is attempting to swim like this. So this is the VMR vector, and if we add the VR vector to VMR vector, we will get the resultant Vm vector. So let me write the magnitude of these. VMR vector has a magnitude V dash, VR has a magnitude V naught. So the resultant Vm will have a magnitude of a square root of V dash square minus V naught square. That is the resultant velocity of the man with respect to ground. So how much time the swimmer is taking in crossing the river in going from A to B? So obviously the time taken by the swimmer 1 is say T1, and that is the displacement upon the velocity in the direction of displacement. So here displacement, we have assumed the width of the river to be d, so that is the displacement. So that is a d upon square root of the velocity of this Vm value, that is the square root of v dash square minus v naught square. So this is for the swimmer 1. Now there is another swimmer. So he has some other ideas to start from A to reach to the B. The swimmer starts from A and he starts swimming towards B. He attempts to swim towards B. So he is starts swimming in this direction. So this is his VMR vector. But because river is flowing in this direction, so the combined effect of him trying to swim in this direction, the river flowing in this direction, will make him actually swim in this direction. So his resultant velocity with respect to ground, which will be the vector sum of VMR and VR. So this is a VR vector and his resultant velocity will be this Vm in this case. So if he starts swimming in this direction and adding the effect of VR, he will actually be swimming in that direction. So he will reach to this point. He will reach to point C on the shore. And when he will reach to the point shore, he starts walking along the shore, not swimming, walking along the shore, and with a constant velocity u such that he reaches to B in the same time as this swimmer reaches from A to B. And this velocity u we have to find. So when he starts swimming, starts attempting to swim along this direction with the addition of that river velocity, so he got drifted along the river. So suppose the drift is, this is the drift that he's got drifted while crossing the river. So suppose drift is x. And also I am taking this direction to be x direction and this direction to be my y direction. Okay. And his total time I am dividing into two parts. So in going from A to C, suppose time taken is t1, and in going from C to B, time taken is t2. So his time of motion is t2 is equal to, obviously this is my equation 1, and his time of motion t2 is equal to t1 plus t2. So let's find t1 and t2. And now see, this VMR is the magnitude of VMR is V dash, and VR is the V naught. So to find time t1 for the motion from A to C, there is no acceleration. So I am using this equation, Sy is equal to Uyt. So actual displacement is AC, so the component of displacement of AC along y direction is just d. So Sy is d, and component of this resultant velocity Vm along y direction is V dash. So Vy is V dash, and time taken from here to here is t1. So this is t1. So how much t1? So t1 would be, so this time t1, this t1 is equal to d by V dash. This is my first equation. And again look, for this motion from A to C, I am writing the equation along x direction, that is Sx is equal to Vx into t. Component of this displacement AC in the direction of river flow, that is the x direction of the drift. So Sx is this x. And this component of this velocity in the direction of river flow is the VR, and the magnitude of VR is V naught, and time taken from here to here is t1. So this drift is, the drift is how much? This drift is V naught into t1, and t1 from here we can write d by V dash. So this is my equation 2. And now to find this t2, to find t2 for the motion C to B. C to B is moving with a constant speed u to cover this distance x. So this time t2 is obviously, the time t2 is the equal to x by u, and the value of x we have just calculated here. and this is the value of x. This is a v naught d by v dash, and then we have to divide by u, and that is our equation. How many equations we have written? 1, 2, this was equation 3, this is equation 4, and this is equation 5 now. And then the total time is t2 is the t1 plus t2. In the question it is given that both streamers start from A, though in different way streams, but they reach to this point B simultaneously. So the total time taken by this streamer is equal to the time taken by this streamer. So T1 is equal to, or T1 is equal to T2, and T2 is the sum of T1 and T2, small t1 and T2. From here I can write the value of T1, equation 1. So T1 is how much? D upon square root of V dash square minus V naught square. T1 here, small t1 here, this small t1 is D by V dash, and small t2 that we've written here is V naught D upon V dash U. So what we can do, we can cancel this t d, and that will become 1 1 1. And here itself we can do some more thing. We can take v dash outside this square root. So if we can take this v dash outside the square root, so that will become v dash, and inside the square root that will become 1, and minus v naught square by v dash square, and this will be 1, and that will be v naught by u, that v dash. Okay, let's write this v dash here and this v dash right now, and then this v dash and this v dash and this v dash will be cancelled. So finally just this will become v naught by u is equal to what it will become, 1 upon, and this thing I can write 1 minus v naught by v dash whole square and power minus 1 by 2 minus 1. So now our u that was asked, so that u will become v naught upon 1 minus v naught by v dash whole square and this whole power minus 1 by 2 minus 1, and this is the answer. So if the man after reaching to C starts walking with this velocity, only then this streamer and this streamer is starting from A, and though moving on a different path, they will reach to the point B simultaneously. Thank you. Today I'll discuss question number 1.8 of Irodov. The question states, two boats A and B move away from a buoy anchored at the middle of a river along two mutually perpendicular straight lines. The boat A along the river and boat B across the river, having moved off an equal distance from the buoy, the boat return. Find the ratio of times of motion of boat tau A to tau B if the velocity of each boat with respect to water is eta times greater than that of the stream velocity. So here what we have to understand that there are two boats. The velocity with respect to river is the same. So both have the same velocity with respect to river. They have the same. And river is flowing with a certain velocity that I will write VR. And the question it is written that velocity of either boat with respect to river is eta times that of the river velocity. And we will use the one equation of the relative motion, that the velocity of boat with respect to ground is equal to velocity of boat with respect to river plus velocity of river. Now let me draw the river. So the river is flowing with a uniform velocity VR, and there is a buoy anchored in the river somewhere here. This is a fixed point with respect to space, and a boat A. There are two boats. Suppose the first boat, let me write the boat 1. The boat 1 starts moving the direction of river like this, and it travels a certain distance, say it travels a distance say D, and then return back. So it goes along the downstream direction and then comes back. So all the thing I am writing with respect to ground. So first let me consider the first boat, that is a boat 1. So when this boat 1 is moving along the downstream direction, the velocity of boat with respect to river is VBR, and if we add the velocity of river, we will get the velocity of boat with respect to ground. So velocity of boat with respect to ground will be the, right now VBR and VR in the same direction, so that will be VBR plus VR. And when it will return back, so this velocity VBR will be in this direction, VR is still flowing this direction. So the vector sum VBR plus VR will have a magnitude VBR minus VR. And VBR is eta times of VR. So we can write this VBR, I can write eta VR plus VR. So that can be written as eta plus 1 VR. And here also, this VBR is eta VR minus VR. So on simplification, that will become eta minus 1 VR. So the total time of motion for this boat 1 for going a distance D and coming back distance D would be say tau A, and tau A during the downstream direction would be D upon eta plus 1 VR, and during the return journey along the upstream direction it would be D upon eta minus 1 VR. We can take D by VR common, so that will be 1 upon eta plus 1 plus 1 upon eta minus 1. Further simplification will give D upon VR, can take LCM. So this LCM, if we multiply this, eta plus 1 and eta minus 1 will become eta square minus 1, and then add them, so what we will get, that will be 2 eta. That is equation 1. And then there is another boat 2. So this distance goes in the perpendicular direction, that of the boat 1. So an equal distance, so the same distance is, it has to go in perpendicular direction as that of the river 1. So it means this is going this way, this is going this way, and the river is flowing this direction, and resultant motion has to be in this direction. So the boat must swim, the boat must row, must be rowed along this direction, and that will be the VBR. On that VBR, if we will add VR, we will get the resultant velocity along this direction. So if the resultant velocity of the boat has to be like this, that would be the VB vector. So that is possible if the boat is rowed along this direction, that is a VBR, and on that VBR, if VR vector is added, then we will get this VB vector. And see, the magnitude of this VBR is eta times, the magnitude of this VBR is eta times that of the VR. So this magnitude is eta times of VR, and this magnitude is VR. So from Pythagoras theorem, this is a hypotenuse and this is a 90 degree. So the magnitude of this VB will be this eta VR whole square minus VR square and their square root. So that would be eta square minus 1 square root into VR. And then the boat has to reach to this buoy, I mean the initial position where this buoy was anchored. So it has to finally come this way, and this is the velocity during the return journey with respect to ground. Let me write this VB dash. This direction is possible. River is flowing this way and resultant velocity along this is only possible if the boat is rowed along this direction. So that should be VBR. If on that VBR, VR would be added, we'll get that direction. So in this case, VBR vector must be like that. So in this case, that is our VBR vector. I mean, this is a different case. So I will write that VBR dash here. And this is a VR. Direction is changed, so I have put the dash, but the magnitude is same. So again, this VBR has a magnitude eta times of VR, and VR has a magnitude VR only. So this, during the return journey, the magnitude of the velocity of the boat with respect to ground will be the square root of this minus square root of this. Sorry, square of this minus square of this and the whole square root. So that would again come out to be eta square minus 1 square root into VR. So for the other boat, boat 2. For the other boat 2, time of motion, that is a tau b. Time of motion tau b. First in going a d distance. That would be d upon the velocity, square root of eta square minus 1 into VR, and in the return journey also same distance d has to be covered with the same velocity, square root of eta square minus 1 plus VR. So during the return journey also, so the time would be the same, eta square minus 1 into VR. So overall time would be 2d by VR square root of eta square minus 1. So we have to find tau a by tau b. So what will be tau a by tau b? So tau a by, this is equation 2. So if we divide equation 1 by equation 2, we will get tau a by tau b. And in both, 2d by VR would be cancelled. So what we are going to get from here, we will get eta upon eta square minus 1, and this square root of eta square minus 1 will go into the numerator. The final answer will be eta upon square root of eta square minus 1, and that would be our answer. Hello dear students, let's see question number 1.9 of Irodov. So this question states boat moves relative to water with a velocity which is n times less than the river flow velocity. At what angle to the stream direction must the boat move to minimize drifting? So this is a problem of river problem from relative motion, and there is a boat and a river. So we know that from the result of relative motion that velocity of boat with respect to ground is equal to velocity of boat with respect to river plus velocity of river. That is number one thing. And then second thing, what is given in the question, that boat moves relative to velocity, water with a velocity which is n times less than that of the flow velocity. So velocity of boat with respect to river is n times smaller than that of the river velocity, or we can also write velocity of river is n times greater than that of the velocity of boat with respect to river. Now let me draw the river. So this is a river flowing with a uniform velocity VR. I assume the width of the river to be capital D, and let the boat moves at some angle theta perpendicular to the direction of river flow. X-axis is the downstream direction, the y-axis is the perpendicular to the downstream direction, and we have to find the angle that this boat with respect to downstream such that drift is minimum. So the angle that we have to find is phi. So phi is basically theta plus pi by 2. So if we can get this theta, we can get also phi. VBR is half of that of the
VR. And this is looking from the ground frame. So if boat will move with respect to ground like that, so it will reach somewhere here. And we know that drift is the displacement of the boat with respect to ground by the time it crosses the river. So it crosses river here and total time taken is say t. So by that time displacement in the direction of river is x, and that is the drift. I can write VBR. I can make a component of VBR. This would be X component and that would be Y component. So the VBR can be written as in terms of I cap and J cap. This is a VBR sine theta because it is in the direction of negative X direction. So we can write VBR is equal to minus VBR sine theta. And this component is the VBR cos theta plus, and this was along the negative x, minus VBR sin theta I cap plus VBR cos theta j cap in the vector form we have written. So let me just remove it just to demonstrate how that has come. And VR, river flow, is in the direction of downstream obviously, and downstream we have taken to be x-axis. So VR is equal to, VR vector is VR I cap. And net velocity of boat with respect to ground is the vector sum of VBR and VR. So if add these two, so what we will get? We will get the first x part, horizontal, component along the x direction, that would be VR plus minus VBR sin theta. So VR minus VBR sin theta I cap, and plus the component along y direction, that is the VBR cos theta j cap. This is the VB. So from here the x component of the velocity of boat with respect to ground is, this is the x part, which is a VR minus VBR sin theta, and the y component of the velocity of boat with respect to ground, that is a VBY is equal to VBR cos theta. So the boat start from here and reaches here. This is the displacement AB vector, and I want to find the time of motion. So I will apply second equation along y direction. There is no acceleration, so displacement is simply velocity multiplied time interval. So displacement along y direction is the velocity of boat along y direction multiplied by time interval. And as it goes from A to B, AB is the displacement, the y component of displacement is, let me write this AC, and AC I have assumed to be D, that is the river width. So D is the displacement boat along y direction. VBY is VBR cos theta, VBR cos theta, and multiplied by time. So from here we will get time to cross river is D upon VBR cos theta. And now I want to apply second equation along the x direction. So second equation along x direction is Sx is equal to VBx into time. AB is a displacement and the x component of displacement is a drift x. So Sx is x, VBx is this, VR minus VBR sin theta, and then multiply this by capital T time interval to cross river, that is D upon VBR cos theta. Simplify a little bit. So we will get VR upon VBR sec theta minus VBR cancel minus tan theta and multiplied by D. Given in the question is the VR is n times of VBR. So in place of VR upon VBR, I can simply write n. So this is n. And now what is given, what is asked, that at what angle the boat should be moved such that drift is minimum, and that angle we have to find phi, and phi is theta plus pi by 2. So to find theta, x has to be minimum. So for x to be minimum, x is a function of theta. So dx by d theta should be 0 if I differentiate it with respect to time. So d will be here. The differentiation of sec theta is sec theta multiplied by tan theta, and differentiation of tan theta is the sec square theta, and this is 0. So here if we d cannot be 0, can take sec theta outside. So that would be n tan theta minus sec theta is 0. And this tan theta can be written as sine theta by cos theta, and sec theta can be written as 1 by cos theta. So this thing will become n sine theta minus 1. So n sine theta minus 1 is 0. Means sine theta is equal to 1 by n. It means theta is equal to sine inverse of 1 by n. So our required answer is phi. So that is a pi by 2 plus sine inverse of 1 by n, and this is the angle made from the downstream direction. So if boat is moved along this angle, so drift would be minimum, and that is our answer.
Let's see this question 1.10 of Irodov. The question states, two bodies are thrown simultaneously from same point, one straight up and other at an angle theta is equal to 60 degree to the horizontal. The initial velocity of both are same, that is v naught, and neglecting air resistance, we have to find the distance between the bodies t time later. The situation that is given to us is, this is a particle say 1. This particle 1 is thrown vertically upward with velocity v naught. And from the same point, another particle, this is particle 2, is also thrown simultaneously. Means suppose the moment of throwing, I can say that is a t is equal to 0, simultaneously with the same velocity v naught, but at an angle theta from horizontal. So what we have to find? We have to find the separation between them t time later. So we can do this in two ways. First thing is to find their coordinates after time t, and then using distance formula we can find the distance between them. And the other method could be to see the problem in the frame of one particle and then find the distance between them. So here I am doing the problem in the ground frame. So the ground frame, I am making this as my x-axis, and let me draw this with a different color. This particle 1 has a velocity v naught, and this direction is the y direction. They are thrown from the origin. So particle 1 will go up something like this, and then it will come back. Suppose at time t, its initial coordinate of both of them are 0, 0. They are thrown from the origin. So look at the particle 1. So obviously the x coordinate of the particle 1 will always be 0 because it is thrown from the horizontal and vertically upward direction. And at time t, suppose it has reached up to here. And this coordinate of this particle 1 is say x1 comma y1 at time t. So particle 1, its position coordinates at time t is say x1 comma y1, and x1 is 0, no doubt, because it is moving in the vertically upward direction, and y1 is the y coordinate, that is the displacement along y direction, and this we can get using the second equation. Acceleration due to gravity is acting vertically downward direction, so that will be, and initial velocity is positive upward, so that would be v naught t plus half minus gt square. This is the first equation. So x1 y1 we have got. And about particle 2, particle 2 will move along a parabolic path like this. The components of velocity of particle 2 are v naught cos theta and v naught sin theta. At time t, suppose it has reached somewhere here at time t, and these coordinates are say x2 comma y2. So at time t, its coordinates are x2 comma y2. And what is x2? x2 is the displacement along horizontal direction, and we know that the horizontal component of velocity and projectile motion is a constant. So this velocity is constant, so in time t the x2 would be simply v naught cos theta into t. That is the second equation. y2 is the displacement along y direction at time t. So displacement along y direction, again using s is equal to ut plus half at square, vertical direction is positive, upward direction positive. So initial velocity along y direction. So basically what I will use sy is equal to uyt plus half ayt square. I will write the second equation along y direction. So this sy, this is the displacement along y direction, that is the y2. So y2 is equal to initial velocity is y component is the v naught sin theta. So v naught sin theta into t plus ay, acceleration always in the y direction. So ay is minus g t square, and that is our equation 3. So at time t, the separation between them is this d. And this d, from the coordinate geometry, we can find the separation between them d as square root of x2 minus x1 whole square plus y2 minus y1 whole square. So x2 minus x1 we will get v naught cos theta t minus 0. So that is just v naught cos theta into t and that whole square, and y2 minus y1. In the y2 minus y1 we can see this half minus half gt square will be cancelled, and what we will get, basically it is a square. So whether you take v1 y1 minus y2 square or y2 minus y1 square, same thing. So that will become v naught 1 minus sin theta into t whole square. If we simplify this thing, so v naught square t square, v naught square t square square root v naught t, that v naught t will come out, and what will remain here, there will be cos square theta t, and there will be 1 plus sin square theta minus 2 sin theta, and cos square theta plus sin square theta will become 1. So we will have v naught t square root of 2 minus 2 sin theta, that will be 2 1 minus sin theta, the whole square root, that is our answer. Hello dear students, let's see question number 1.11 of IE Irodov. So this question states, two particles move in a uniform gravitational field with an acceleration g vector. At the initial moment, the particles were located at one point and move with velocity v1 and v2 horizontally in the opposite directions. Find the distance between the particles at the moment when their velocity vectors become mutually perpendicular. So let me draw a good diagram for this problem. So here are two particles, particle 1 and 2. At t is equal to 0, they are launched from the same point horizontally in opposite direction with velocity v1 and v2. And this is a horizontal direction assumed to be x direction, the direction of motion of particle 1, and vertically downward direction I've assumed to be y, and the acceleration is uniform, that is g. So for the both particle, what is same? So if I talk about for the both particles, initial component of the velocity along y direction, because they both are launched in the horizontal direction. So for both particles, initial component along y direction is 0, and acceleration is always vertical downward direction and uniform. So for both particle, the y component of acceleration is plus g, started from the same point, same position. So if we apply second equation along y direction, sy is equal to uyt plus half ayt square. Uy is 0, ay is same. So at any moment, their displacement from the beginning would be the same along y direction. So in any time interval, they will be falling by equal amount along y direction. So if they start from the same position and fall down by equally, so at every moment they will be at the same horizontal level. So suppose they start from here. Now at some future moment, if we draw the trajectories, so it is, this particle is moving like this, and this particle is moving like this, and this is moment t is equal to 0. So at a later moment, they will be at same horizontal position. So particle 1 would be somewhere here, and now suppose this velocity has become v1 dash vector. This moment is t is equal to t, and this particle reaches here and its velocity has become v2 dash vector, and we can find the components of this velocity. The horizontal component of velocity remain constant, so this component will still be v1, and vertical component will find the horizontal component of velocity of particle 2 at time magnitude would be v2, and the vertical component we will find. We know that velocity along y direction is equal to initial velocity along y direction plus acceleration along y direction time t. Both had the same 0 initial velocity along y direction. So at any future time, their velocity along y direction will be gt, because ay is g. So this component would be gt for the particle 1 also and gt for the particle 2 also. So velocity vector v1 dash of particle 1 at time t is, I want to write in terms of I cap and j cap. So this is a v1 I cap along x direction plus gt
j cap, this part is along y direction, and for the particle 2, v2 dash is because I've assumed right direction to be positive x direction, so this is this velocity I will write minus v2 I cap, and the y component is the gt j cap. And we have to find at what time these vectors have become perpendicular. So when v1 dash is perpendicular to v2 dash, their dot product would be 0. So v1 dash dot v2 dash would be 0, and v1 dash dot v2 dash I can write here. So v1 dash dot v2 dash, v1 dash dot v2 dash is equal to v1 I cap plus gt j cap dot minus v2 I cap plus gt j cap. This will become v1 into minus v2, that is a minus v1 v2, and plus g square t square is 0. So what we will get, t is equal to v1 v2 by square root of v1 v2 by g, and this is the time after which the velocity vector will become perpendicular to each other, and we had to find the distance between them at that moment. We can find directly because in air there is no relative acceleration, so a relative is 0, and initial relative velocity of particle 1 with respect to 2 or particle 2 with respect to 1, so the magnitude of the relative velocity with respect to 1, the relative velocity of 2 is v2 plus v1, and the magnitude is same either with respect to 1 or with respect to 2. So magnitude of the relative velocity of each other is v1 plus v2. So relative separation between them at time t would be the magnitude of relative velocity into time interval, because there is no acceleration, so that is just v relative into t, and v relative is v1 plus v2 multiplied by this time interval, so that is v1 v2 and divide by g. So this would be the separation between them at time t, and we can see from the diagram, this is nothing but this separation. This is s relative, and we can do from the ground frame also. This v2, this length would be simply v2 into t, horizontal displacement of the particle 2 in time t, and this separation would be v1 into t, horizontal displacement of particle 1. So overall separation will be the v1 plus v2 multiplied by t, and which we have got it directly from the relative motion concept. So this is our answer. Hello dear students, let's see question number 1.12 of IE Irodov. This question states 3 points are located at the vertices of an equilateral triangle whose sides equal a. They all start moving simultaneously with velocity v constant in modulus, with the first point heading continually for the second for the third, and third for the first. How soon will the points converge? So it's very good question of a relative motion. So let's see. So this is an equilateral triangle, and there are 3 particles, 1, 2 and 3, initially situated at the 3 vertices of this equilateral triangle. This equilateral triangle is of side A. So particle 1 always continually aim toward the particle 2. So this is always moving like this. At the initial moment it is moving like this. So particle 1 is aimed towards 2, and particle 2 always aim towards particle 3, the speed is same v, and this particle 3 is always aim towards particle 1. This is just the initial speed, initial velocity, and they will continuously update their direction such that 1 will be always towards heading towards 2, 2 will always head towards 3, and 3 will always head towards first particle. So now after a very little time, in the diagram I will show a bit long displacement, otherwise the diagram will not be clear. But after a very little time interval, suppose a particle reaches here 1, and particle 2 reaches here, and particle 3 reaches here. So obviously starting from the same moment, the speeds are the same, so they will cover equal distances. Now the figure joining them would be like this. This would be the new shape joining them. This length, and this length is same, because they are moving with the same speed, and at the same time they will cover the same length. So initially, if the figure joining them is an equilateral triangle, so right now also it is equilateral triangle. Now what will happen to the velocity of 1? 1 has reached here, 2 has reached here, and 1 has always moved towards 2. The direction of velocity of particle 1 will now be like this, and direction of velocity of particle 2 will like this, and direction of velocity of particle 3 will like this. And then similarly, after a little more time, 1 will reach somewhere here, 2 will reach somewhere here, 3 will reach somewhere. Again they will cover equal distance in equal time. So now the shape joining them would be this shape, and this will also be equilateral triangle, because in equal time they have covered equal length. Now the velocity of particle 1 would be like this, velocity of particle 2 would also be like this, and velocity of particle 3 will be like this. And this I have shown after a finite interval, but this continuously bending of the direction is happening continuously. So if I make a continuous path, so particle 1 will continuously bend something like this, and particle 2 will continuously bend something like this, and particle 3 will continuously bend something like this. And now it is apparent, because from the symmetry of the problem, they all will meet at the centroid of this triangle, obviously simultaneously from the symmetry of the problem. So we want to find the velocity of separation between any two at a general time, at any time. So suppose at time t, this is the figure. So in this figure, this is the equilateral triangle like this. The velocity of particle 1 was like this, and velocity of particle 2 is like this, velocity of particle 3 is like this. This angle is 60 degree, this angle is also 60 degree. So I am choosing particle 2 and 3. Want to find the velocity of approach between them. So to find the velocity of approach, we need to make components of velocity along line joining them. So this component would be v cos 60, that is a v by 2, and that component would be v sin 60, that would be v root 3 by 2. So what is the velocity of approach between 2 and 3? So this velocity of approach at a general moment is relative velocity between them along line joining them. So that was a v plus v by 2. So v plus v by 2 would be 3v by 2. And because at any moment the figure joining them is equilateral triangle, so this v approach is constant. And this v approach is the velocity approach between any two particles. And we know that if the velocity of approach is constant, mean the particles are approaching at a constant rate, Then time of collision. Time of collision is the initial separation divided by constant magnitude of the velocity of approach, and I want to find at what time particle 2 and 3 will collide. The initial separation was A, that was the length of the side of the equilateral triangle, and velocity of approach is 3v by 2, so this is 2a by 3v, and at this time particle 2 and 3 will collide because all the particles are colliding simultaneously. So at this time particle 1 will also collide. So this is the time after which all the three particles will collide. So that answer is 2a by 3. Hello dear students, let's see question number 1.13 of IE Irodov. So this question states point moves uniformly with velocity v so that the velocity vector v vector is continuously aimed at point B, which in turn moves rectilinearly and uniformly with velocity u, and the magnitude of u is less than magnitude of v. At the initial moment of time, v vector is perpendicular to u vector and points are separated by a distance L. How soon will the points converge? So as it is given in the question, there are two particles A and B. So particle B moves rectilinearly, and let me assume that it is moving along x direction. This is particle B and its velocity is like this. So velocity of B is given to be u, and this is a constant moving along the x direction. There is another particle A, and this particle was initially at separation L from B, and its velocity vector is v, and the initial velocity vector was perpendicular to the initial velocity vector of B. So its initial velocity is v in this direction. Magnitude is constant, given in the question that v is more than u, and this particle always heads towards B. B is moving the same direction always along x direction, and so A is continuously updating its direction such that A is always towards B. So suppose in some time, in a very small time, B reaches here, maybe somewhere here, in a very small time B reaches here, A reaches here. Now the line joining them would be this. So what A will do? A will update its direction. So now A has always to be towards B. Then after a little more time, suppose B reaches here and A reaches here. So line joining A and B is like this. So A will again update its direction like this. Little more time, B reaches here, A reaches here. Again line joining them would be like this. So now the velocity would be like this. So continuously A will keep on updating, and A will keep on updating its direction so that A is always heading towards B. And this I have shown in a finite interval time, and this updation is going on continuously. So if we draw the path of A, so path of A would be a curved path, and this path would be something like this, and eventually it will meet B somewhere here. This was at t is equal to 0. At t is equal to 0, B was here, A was here. Now at a later time, say at time t, at time t, A has reached here. Its velocity is v vector, and this is direction is changing but magnitude is constant. This is at time t. At this moment, A must be here. Sorry, B must be here, because A has always B moving towards B. No, its velocity is u. So I want to further extend the direction of line joining A and B at time t. This is the line joining A and B at time t. Suppose this angle is theta. I can draw it in another diagram. Here, this is A and this is B. Velocity of B is u. Velocity of A is v. This angle is theta. I can make component of velocities along line joining them. So obviously this velocity is totally along this line, so no component. So this would be a u cos theta, and this component would be u sin theta. So at time t, a velocity of approach between A and B. Velocity approach between A and B is the v minus u cos theta. And we know that velocity of approach is the rate at which the separation between the two particles decreases, or the rate at which the two particles approach. So suppose separation between A and B at time t is SAB. So that is minus dsAB by dt. So we can write dsAB is equal to minus v, just want to keep minus here only, no problem. So v minus u cos theta dt, integrated for the whole motion. Initially at t is equal to 0, the separation between them was L, that is the initial separation. Here SAB is L, and when they will collide, say at time capital T, when they will collide, obviously the separation will become 0. So separation will become 0. So now this integration will become simply L. Magnitude of V and U are constant, but theta is variable. So if we integrate this, so this part integration will become simply Vt, and U will come outside, but theta is variable, so that cannot be taken outside of the integration sign. So I will write this 1. What we have to find? At what time they will meet, converge. Time of collision we have to find. Okay, we have to find t. And now I will take another result. This angle, the velocity vector make an angle theta from the x direction. So here I am making a line parallel to x-axis. So this velocity, this angle will also be theta here. So if I make x component of the velocity of particle A, that is a VAX. So VAX is a V cos theta. One important thing to observe it. So they started like this. So initial x coordinate is 0, and finally they will have same x coordinates. So it means the displacement of both A and B along x direction when they will collide will be equal. So this is the displacement of B along x direction when they will meet, and this is the displacement of A along x direction, but its component along x direction is same. So what we can say that when they will collide, they will have same displacement along x direction. Displacement of A along x direction is equal to displacement of B along x direction.
So displacement of A along x direction will be the integration of velocity of A along x direction dt for the whole time, and because velocity of B is constant, that is u, so that will simply be u into t. And this integration is, I will put the value of Vax, that is a v cos theta from 0 to t dt is equal to u by t. This v will go outside, so we will go outside, so we'll remain here with cos theta dt 0 to t, and this is ut, and I can take this v here, so this will be v ut by vt, ut by v. I can put this value in the equation 1 now. So L would be Vt minus u. This integration we have found in the equation 2, and this integration we have got the value of this integration ut by v. Simplify this, that would be v square, and there is one u also outside, so that would become u square. So v square minus u square by v, and this whole multiplied by t. So time when they will meet is vl divided by v square minus u square, and this is our answer. Today I will discuss question number 1.14 of IE Irodov. So this question states a train of length L meter, L is equal to 350 meter, starts moving rectilinearly with constant acceleration W. T time after the start, the locomotive headlight is switched on. That is a event 1. And tau time after that event, the tail signal light is switched on. This is the event 2. Find the distance between these two events in the reference frame fixed to the train and to the earth. How and to what constant velocity relative to the earth must a certain reference frame k move for the two events to occur in it at the same point? So I've converted the information given in the question into a diagram. So this is a line, so x-axis. Along this line, this locomotive of length L is moving. Start from the rest. So initial velocity is 0 and it is moving with a constant acceleration. I can write W. I would have liked to write A, but okay, as it is given the question, W. Starting from the this rear end is x equal to 0. The first event is the switching on the headlight at time t from the starting. So this front edge of the train has moved by that time by amount x1. Using first equation of motion, I can write x1 is equal to ut plus half at square. So initial velocity 0, acceleration is w, so wt square. So x1 is half into wt square. This is my equation 1. And tau time later mean from the moment this headlight is switched on, tail light is switched on. So starting from initial moment t is equal to 0, that time moment is t is equal to t plus tau. The rear headlight is on, switched on. So what is the this end has traveled how much? If I start from here, the initially this end was here, now this end has come to here. The displacement of the rear end by the time the rear end switch headlight is on, that is x2. Again I will use ut plus half at square, initial velocity is 0. So directly I can write that will be half into acceleration into time interval whole square. Time interval from beginning to here is t plus tau. So omega, half omega t plus tau whole square. That is our second equation. So what was asked that? Find the distance between these two events. It should be a better framed. Event is a time. So what does it mean? That distance between the positions where these event occurred
and the reference frame fixed to the train and to the earth. So I am looking from the ground frame, so in the frame of earth, at this position the headlight was on, switched on. At this position the rear end light was on. So distance between them is d. Distance between the point at which this event took place is d. So from the geometry you can say that this d is equal to this x2 minus L plus x1. So d is equal to x2 minus x1 plus L. So d is equal to x2 minus x1 plus L. So I can write this x2 minus x1 minus L, and x2 minus x1 from equation 1 and 2 I can take omega by 2 common. So omega by 2 I can take common. What I will get? T plus capital tau whole square minus t square and minus L. And I can use a square minus b square is equal to a plus b into a minus b. So we will get omega by 2t plus tau and multiply by tau and minus L. Magnitude of this distance. So the magnitude of this distance will be, if this comes to be positive, that is fine. If it comes negative, we can simply write L minus omega by 2t plus tau. So that is our answer for the first part. Now the second part, what is asked, how and with what velocity a certain reference frame move for these two events must occur at the same time, same position. So suppose there is another car, and this car is moving with velocity v, and these events have occurred at this position, this position. The time interval between these two events is tau, and the position difference between these two events is this mod d. So the velocity with which it should move, that should be the separation between the two events divided by time interval. So putting this value, we will get L minus omega by 2t plus tau and divide by tau, and simplify, we will get the answer. We can leave answer this way or just put the numerical value. In this video, I will discuss question number 1.15 of IE Irodov. So this question states, an elevator car whose floor to ceiling distance is equal to 2.7 meter starts ascending with constant acceleration 1.2 meter square. 2 seconds after the start, a bolt begins falling from the ceiling of the car. Find bolt's free fall time and displacement and distance covered by the bolt during the free fall in the reference frame fixed to the elevator shaft. The first part was the falling time of the bolt. So we know that the time interval between two events is invariant of the frame of reference in classical mechanics, and it will be easier for me to solve in the elevator frame. So it was given that it start, and after some time, after 2 seconds after the start, bolt start falling. In the ground frame, by that time this elevator would have get some velocity, would have achieved some velocity. But if we talk about the elevator frame, there is a bolt here and it start falling. So with respect to the elevator, what is the initial velocity of the bolt? It just started falling. You can think of your room as elevator. Earth is moving, so with earth it is also moving. If something from the top falls, what is the initial velocity of that thing with respect to room? Obviously 0. So with respect to this elevator, at any time this bolt falls, so initial velocity of the bolt is 0. Acceleration of the elevator is a naught. And if we have to find the acceleration of bolt with respect to elevator, I am writing elevator as a lift. So in the vector form, that would be AB minus AL, and all the motion is along this vertical line, so direction part can be done. with positive or negative. So I'm just removing this vector sign, and direction part I will take care by plus or minus. Suppose this downward direction is positive. So if I take downward direction of positive, acceleration of the bolt with respect to ground, anything which is in air, acceleration with respect to ground is g, downward. So this acceleration is g downward, and this acceleration is minus a naught, because I have taken the downward direction as positive, so that is a minus a naught. So actual acceleration will be g plus a naught. And let me write the magnitude. This magnitude would be 9.8 plus 1.2, so that is our 11 meter per second square. And in the frame of elevator, I will apply the second equation. Second equation, S is equal to ut plus half at square. So with respect to this elevator, started from here, and when it will strike the floor, it will reach here. So distance traveled is L, and L is 1.2 meter. So in place of S, just write L 1.2. Initial velocity is 0. Acceleration of the bolt with respect to elevator is 11. So that is a 1 by 2 into 11 into t square, and so t would be 2.4 by 11 square root. Check this answer. So you will get answer 0.7 second. And now for the second part, let me draw a diagram again. Now look the problem in the elevator shaft frame. Elevator shaft frame is basically a ground frame. So I have drawn another diagram. This is a relatively smaller diagram. So the elevator starts from rest with 0 velocity and the acceleration half 1.2 meter per second square. And after time 2 seconds, the bolt was started falling. So by that time, looking from the ground frame, this is a ground frame picture. So elevator would have achieved some velocity. So that velocity I can write using the equation v is equal to u plus at. Initial velocity is 0, acceleration is 1.2, and time is 2. So this velocity is 2.4 meter per second. And I am starting another stopwatch from this moment, because this is the moment this bolt start falling. So with respect to elevator, the initial velocity of the bolt was 0. So bolt velocity with respect to ground is same as that the velocity of the elevator in the ground frame. So initial velocity of this bolt at this moment, I have started new stopwatch. This time moment is t dash equal to 0. So this initial velocity is equal to the velocity of the elevator at that moment. So that is 2.4 meter per second. And once the bolt left the contact with the elevator, it is only force acting on it is acceleration due gravitational force. So its acceleration is g downward. So now the bolt is moving under gravity. So velocity is upward and acceleration is downward. It will go first up and then come down. So what we have to find? We have to find the displacement and distance covered by the bolt during the free fall. And the first event was falling of the bolt from the top, and the second event was hitting the bolt with the floor. And we know that distance between any time interval between any two events is same in all frame of reference. So this time interval in the elevator frame was 0.7. So when this will hit, so this time interval also be 0.7. So this time moment is t dash equal to 0.7. So by this time displacement of the bolt, we can directly write displacement of the bolt from the second equation. So for displacement, I am writing equation S is equal to ut plus half at square, and taking upward direction positive. So if I take upward direction positive, u will be plus 2.4, and time is 0.7. Acceleration will be, because it is downward direction and upward is positive, so it will be minus 9.8 into time whole square, minus 0.721. What does it mean? That it means that the bolt has come down below the point at which it from where it left. So minus sign tells that. Now what is the total distance traveled by the bolt? So what we will do, we will first calculate this distance
and up to here, then from here to here. So if I calculate this distance, let me call this distance to be, say, h. This is h, and this is a, and this is b, and this is c. Using third equation from here to here, I can directly get h is equal to u square by 2g. So let me put these value. U is 2.4 and g is 9.8. I will get 0.29 meter, and I'm drawing diagram again using the interpretation of this negative sign. The bolt started off from this point, goes up to this distance h, and will come down because finally displacement is negative, so final point is below this point, and this distance is the magnitude of this displacement, which is 0.721. So overall distance is, this is h and this is h and this is 0.721. So I can write total distance is 2h plus 0.721 means 0.58, double of this, plus 0.721, 1.3 meter, and which is our answer. In this video, I am going to discuss question number 1.16 of IE Irodov. So this question states, two particles 1 and 2 move with constant velocities v1 and v2 along two mutually perpendicular straight lines towards intersection point O. At the moment t is equal to 0, the particles were located at the distances L1 and L2 from the point O. How soon will the distance between the particles become smallest, and what is it equal to? So let's draw a good diagram first. So these are the two mutually perpendicular lines, and this is intersection point. Particle 1 is moving with velocity v1, particle 2 is moving with velocity v2 towards intersection point. Initial separation from O of these particles were L1 and L2, and they are moving with constant speed. So say after time t, this particle reaches somewhere here. So how much distance it will travel, because it is moving with a constant velocity, so distance traveled by this is a v1t, and distance traveled by this particle would obviously be v2t. So if I join them at time t, this is a line joining them at time t after the start, and suppose distance between them is s after time t. So s is equal to, using Pythagoras theorem, this side is square plus this side is square, and this length is L1 minus Vt and this length is L2 minus Vt. So distance between them at time t is s, and s square is equal to L1 minus V1t whole square plus L2 minus V2t whole square. So at what time separation between them will be minimum, and to find that it will be minimum when s is minimum, and s is minimum when s square is minimum. So I can just differentiate this equation with respect to time. So for s to be minimum, s square is also minimum. So what I will get, ds square by dt. If I differentiate this equation, what I am going to get with respect to time, twice of L1 minus V1t, and go inside the bracket and then multiply by minus V1. Similarly, this part integration will give twice L2 minus V2t multiplied by minus V2, and this is equal to 0. So let me multiply this thing. So I can take 2 common, in fact minus 2 common I can take. So L1 V1 plus v1 square t from this side L2 v2 minus, actually this will be minus because that minus I have taken outside, minus v2 square t, and this is 0. So v1 square plus v2 square into t is equal to L1 v1 plus L2 v2. So the time at which the separation will be minimum that we've got is equal to L1 v1 plus L2 v2 and divided by v1 square plus v2 square. And what is the minimum separation? And to find the minimum separation, what I need to do, I need to put this value of t into this first equation. So then I will get S minimum. So minimum separation, S minimum is S at, and let me call this time to be set, this t is equal to this time to be t naught. So S at t is equal to t naught, here I can put, and on putting this thing I will get L1 v2 minus L2 v1 mod divided by square root of v1 square plus v2 square, and this is answer to this question. I am going to discuss this question 1.17 of Irodov. What does this question say? It says from point A located on a highway, a figure is given. One has to get by car as soon as possible to point B located in the field at a distance L from the highway. It is known that the car moves in the field eta times slower than on highway. At what distance from point D one must turn off the highway? So this is the diagram as it is given in the question. This is a highway and this is a field. Velocity of the car is eta times slower in highway as compared, eta times slower in the field compared to that of highway, and A, D and B are fixed points. So we have to find, the driver has to start from A and reach to B, and he has to come out of the highway, get off the highway and enter to the field, only then he will reach to B. So he has to choose at which point he has to come down from the highway to the field such that time taken is minimum. So suppose he's come down to the field at point C, which is at a distance say x from the fixed point D, and this is what we have to find. Because A and D are fixed points, I am assuming the distance between A and D to be some A, or I can write capital D. That is a fixed thing. If velocity on the highway is v, so velocity on the field is eta times smaller, so velocity here is v by eta. And using Pythagoras theorem, the length of the path in the field will be the square root of this length will be square root of x square plus L square. So total time of motion t is equal to time taken from A to C plus time taken from C to B, because car is moving with a constant velocity, so time taken is just the distance upon speed. So this time t A to C, this length would be how much? This length would be d minus x, or d minus x divided by the speed in that part, which is v. And time from C to B is the distance upon velocity again, that would be distance as square root of x square plus L square, and velocity is v by eta, so v by eta, and eta will come here. So what I can take 1 by v common, will get d minus x plus eta square root of x square plus L square, and we have to find what is the value of x as that this time is minimum. For t to be minimum, dt by dx, because t is a function of x, dt by dx must be 0. So we'll differentiate this equation with respect to x. So 1 by v from constant multiple will remain outside. Capital D is a constant, its differentiation will be 0. This differentiation will be -1. Here I can eta outside. To differentiate this, what I will get, 1 upon 2 square root of x square plus L square, and go into the square root. What we'll get 2x, and this has to be 0. So this 2 and 2 will get cancelled. So simplify this thing. We are going to get 1 is equal to eta x divided by x square plus L square. We can square both sides. So if we square both sides, what we are going to get, 1 is equal to eta square x square by x square plus L square. Further simplification will give eta square x square is equal to x square plus L square. So can take all the x on one side, so that would become eta square minus 1 into x square is equal to L square. So finally we will get x is equal to L upon square root of eta square minus 1. So this is the distance from D at which, if this driver turns, he will reach from A to C and A to B. Today I will discuss question number 1.18 of Irodov. This question states, a point travels along the x-axis with a velocity whose projection Vx is presented as a function of time by the plot. This is the graph I've already made. Assuming the coordinates of the point x equal to 0 at the moment t is equal to 0, draw the approximate time dependence plots for the acceleration omega x, the x coordinate, and the distance covered. So this is the x component of velocity variation with time, and we have to plot variation of the x component of acceleration, x coordinate, and distance traveled. I have plotted, already made the graph, and I want to draw all these things in a single graph. For the acceleration, I'll use the red color. This is for acceleration, x component, and we know that acceleration is the rate of change of velocity with respect to time. So the x component of acceleration is equal to d by dt of vx. We know that if we have a yx graph and the graph is like that, at any point if I make a tangent to this graph, the slope is dy by dx. So in the vxt graph, that is the slope of vxt graph. And we know that if acceleration, if the acceleration is constant, slope is a straight line. So looking from here, we have in fact few straight line. This is a part AB, this is BC, this is CD, and this is D, all the straight parts. And the straight part mean they have this constant slope. So in all these parts AB, BC, CD, DE, we will have the constant acceleration, though the magnitude in different part will be different. So looking to the part AB, so its slope is delta y by delta x. Delta y is 1 and delta x is also 1. The slope, magnitude of slope here is 1, constant 1. So from here to here, if I make the graph of acceleration, so magnitude of acceleration and the direction also remain constant. So that is this part, the acceleration would be like this. In the part BC, Vx is constant. Constant mean its derivative is 0. The slope of part BC is 0. So in the part BC, the slope would be
from 1 to 3 the slope would be this 0, like this. And then part CD, that is if you look, it makes an obtuse angle from the time axis, so its slope should be negative. So first of all, let me get the magnitude of the slope. So delta V by delta X, this delta V, this magnitude is 3 and this magnitude is also 3. The magnitude of slope is 3 by 3, that is a 1, because it is making obtuse angle, so the slope is -1. So from C to D, mean from 3 second to 6 second, the acceleration would be -1. And then from D to E, this is a positive slope and delta y is 2 and delta x is 1, so magnitude of slope for this part is 2. So this is a graph for the acceleration, x component of acceleration, which I have made by red color. And now the x coordinate, that is because it has started from the origin, so x coordinate is same as the displacement. And we know that in the velocity time graph, the area under the curve gives the displacement. So let me write for this part the area is 1 by 2. So in 1 second it will reach to coordinate 1 by 2 here. And then this part area is 2. So increase the area by 2, mean the displacement will increase by 2 more points. So here the displacement at the end of this, that will become 2 and 1.5, so that will be 2.5, it will be somewhere here. And now further, this area is also 0.5. So now at the end of the 4 second, total displacement would be 3. And now area is becoming negative, and also at this moment Vx is 0, so the displacement time graph slope is velocity, so slope should be 0 there. And then for this reason, for 5 to 6, this area, this is 2, this is 2, so for this part displacement is -2, 2 into 2 is 4 and half is -2, so we have to decrease the displacement by 2, so at the end of time t is equal to 6, displacement will be 3 minus 2, that would be 1, somewhere here. And finally the displacement of this part is, this is 2 and this is 1, that is just 1. So the displacement here would be 1 less, that will be 0. And if we check the overall area, so this area is 0.5, this area is 0.5, 0.5 is 1, and this area is 2, so this is a +3, and this is your 3, and this is 2, 3 into 2 by 2 is 3, and because it is on the negative side, so overall displacement is 0. So now we have to make these points with a suitable graph. In the part AB, we can write the equation s is equal to ut plus half at square. Initial velocity is 0. So for this part, this is an upward parabola, something like this, so that would be like this. And then this part BC, velocity is constant, and we know that Vx is equal to dx by dt. So the slope of xt graph is the velocity, because velocity is constant, so slope is constant. So for this part the graph will be simply a straight line, and here slope has to be 0 because here velocity is 0, so now it will bend something like this. And because there is a constant acceleration for this part for C to D, so that this thing would be going continuously like this. And finally, because there is acceleration, so this graph would be like this. So this is the graph for the position or the x coordinate. And now we can make a plot of the distance traveled, because we know that distance can never decrease and it is never negative. So till displacement is increasing, distance graph is same as that of the displacement. So up to 4 seconds, the distance graph would be the same. Now here the displacement has got decreasing because this is a turning point, but distance will be keep on increasing. So in making graph, what we will do, we'll just make a mirror image of this part from about this line. So this graph will look like here and here though. So this graph will look like something like this. That would be our distance time graph. So this is for the distance.
Today I'll discuss this question number 1.19 of Irodov. This question states, a point traverses half a circle of radius r during time interval tau. Calculate the following quantities average over that time. Mean velocity. Here this author mean velocity, that average speed, and looking by the symbol. And B, the modulus of the mean velocity vector. And C, modulus of the mean vector of the total acceleration if the point move with constant tangential acceleration. So this is a circle of radius r. A particle start at t is equal to 0 for initial velocity 0 and a constant tangential acceleration. After half revolution, the time is tau, the particle gets some velocity v, suppose. So we have to find first the mean velocity. Mean velocity here, again I repeat that the symbol is something like that. So that is a scalar symbol. So what does it mean? That is the average speed. And we know what is the average speed. Average speed in any interval is total distance divided by total time. Divided by total time. So for half cycle, the total distance is the half the circumference, so that is just pi r, and time from here to here is tau. So average speed is simply pi r by tau. And then we have to find the modulus of the mean velocity. Modulus of the mean velocity mean this is a velocity vector, its modulus. So that is what we call normally average velocity, magnitude of the average velocity. So this is the magnitude of average velocity, and we know that average velocity is displacement upon time interval, displacement divided by time interval, and we have to write the magnitude of displacement here because magnitude of average velocity is asked. So from here to here, the displacement is 2r, the magnitude of displacement is 2r, and time interval is tau. So this answer is 2r by tau. And finally, what is asked? The modulus of the mean vector of the total acceleration. So total acceleration is omega, its modulus, its mean, modulus of its mean. So we know that this is basically average acceleration and the magnitude of average acceleration. So average acceleration is the change in velocity divided by time interval, and then I will have to put the magnitude here. So to find this speed at this point, it is moving with a constant tangential acceleration. I can use the equation s is equal to, along the length I am using, s is equal to u plus v by 2 into t. This is the second equation. So along the length, it has traveled a total distance, how much? Pi r. Initial velocity was 0. Suppose when it covered half circumference,
the velocity has become v and time interval is tau. So from here I can write this v is equal to 2 pi r by tau. This is the speed after half revolution. So initial speed is 0, final speed is at time tau, 2 pi r by tau. So change in velocity is basically change in speed because initial velocity was 0. So the change in velocity is simply 2 pi r by tau, and time interval is also tau. So divide by tau, so that would be 2 pi r by tau square, and that is our answer for the radius vector of a particle varies with time t as a r vector is equal to a vector multiplied by t into 1 minus alpha t, where a vector is a constant vector and alpha is a positive factor. Find the velocity v and the acceleration w of the particle as a functions of time, and also the time interval taken by the particle to return to the initial points and the distance s covered during that time. So the position vector given is vector r is equal to a vector into t 1 minus alpha t. Alpha is a positive constant and a is a constant vector. Suppose this vector is like this is a vector. So this factor can be positive or negative. So this is a scalar multiple of vector. So when this factor is positive, r vector is in the direction of a, and when this factor is negative, this r vector is opposite to a. So now we know that velocity is the rate of change of position with respect to time. The velocity vector at any time in the instantaneous velocity is the rate of change of position with respect to time. So this I can write like t minus alpha t square multiplied by a vector. Like we have rules for the product rule for the scalar, similarly for the vector, if I have to differentiate some lambda a, so I will apply product rule the same way as we normally apply. So that will be lambda dA vector by dt plus a vector d lambda by dt. If a is a constant vector, so this factor will be 0, null vector. So the answer will be simply a vector d lambda by dt. So here a vector is a constant vector, so when we will differentiate it by constant multiple rule, a will come outside, and then we have to only differentiate t minus alpha t square. So this differentiation will become a as a constant, and that would be 1 minus 2 alpha t. Again it is a scalar multiplication of vector. This is scalar, this is a vector, so v vector is along a if this vector is positive, and v vector is opposite to a if this vector is negative. So it means there will be some turning at certain moment. So suppose let me draw it again. This is a direction of a vector, and in the beginning initial velocity, so initial at t is equal to 0, the velocity would be the initial velocity. So initial velocity, I will put t is equal to 0 here. So what we will get, the u will be just a vector, and suppose this is the line along which the particle is moving. So initial vector is in the direction of a vector. This is the direction of the initial vector, like this, u vector, which is in the direction of a, and the magnitude of initial vector is simply a. There will be moment when this particle will take a turn, because after some time direction of this v vector will become negative. So we would like to find at what time this particle turns. Suppose it take turn at t is equal to t. So at that time v will become 0, and v will become 0 when this factor is 0. So this factor is 0 mean at, if I equate this to be 0, what I will get? T is equal to 1 by 2 alpha. So at t is equal to 1 by 2 alpha, this will come to momentary rest, and then it will turn back and it will reach to initial position after some time. So when it will reach to the initial position, is in the beginning r was 0, and when it will reach to the initial position, so when particle reaches initial position, mean it will have same position coordinate as it had initially. Initial position coordinate was 0, and after some time its position coordinate will again become 0, so i.e. r is 0. So this r is 0. If we solve this, r is equal to, this will again be 0 when this factor is 0. So i.e. t1 minus alpha t is 0, so it will have two solutions. One is t is equal to 0, obviously that was initially, and other solution is t is equal to 1 by alpha. So it will reach to initial point after double the time it comes to a momentary stop. So it will reach here at t is equal to 1 by alpha. Now what were the other parts? So we had to also find the acceleration w. So acceleration w I can write for the acceleration part. Now I can erase this part. For the acceleration w, acceleration is the rate of change of velocity with respect to time, and velocity as a function of time we have calculated this. So acceleration will be a vector by constant multiple will come outside, and differentiation of this part will simply be minus 2 alpha. So that will be minus 2 alpha a. Alpha is a positive constant, so it means the acceleration is uniform and opposite to the initial velocity, like this. So that is a fit case for a turning. And then we have to find the time interval taken by the particle to return to the initial points. So it started here and reaches here. So for the part B, that time interval is simply 1 by alpha. And we have to also find the distance s covered during that time. So from the symmetry, if I can calculate this length, say this length is d. So overall distance traveled to reach to the initial point is the twice of d, and the magnitude of d is nothing but the magnitude of this position vector at t is equal to 1 by alpha. So what is d? What is d is the mod r at t is equal to 1 by 2 alpha. So I am putting the value. So that is a mod a vector, and in place of t I will write 1 by 2 alpha and 1 minus alpha into t 1 by 2 alpha. So how much that would be? Mod a vector divide by 2 alpha, and this is 1 minus 1 by 2 is 1 by 2. So that is a 1 by 4 alpha multiplied by mod a. So the required answer, the total distance traveled by this particle of when it reaches to the initial point again, that answer is twice of d. So twice of d is mod a divided by 2 alpha, and that is our answer. Thank you.